Today we are going to discuss some fundamentals about theory of machines. In theory of machines, we are mainly dealing with mechanisms and machines. So, what is a mechanism? Mechanism is a set of machine elements arranged in a specific order to produce a specific motion. It transmits or modify a motion. Examples are slider crank mechanism, typewriter, spring toys, etc. Now, here we mention machine elements or kinematic link. So, a part of a machine having some relative motion with respect to one another is called machine element or a kinematic link. A link should be a resistant body. So, what is a resistant body? It is a body which is not a rigid body but acts like a rigid body while functioning in the machine. In actual case, no body is the rigid body as there is always some kind of deformation while transmitting force. Now let us move on to type of links. Links can be classified based on deformation and provisions. Based on deformations, they are classified as rigid link, flexible link and fluid. In a rigid link, deformations will take place during the transmission of forces or motion, but the amount of deformations are negligible. For example, crank, connecting rod, piston. In a flexible link, deformations are not negligible but permissible to some limits. For example, belt, chain rope, etc. In a fluid link is one that is deformed by having fluid in one closed vessel and the motion is transmitted through fluid by pressure. Example, hydraulic press. Now, based on provisions, links are mainly classified as binary links, ternary links and quaternary links. Next one is the type of relative motion. There are mainly three types of constrained motion. They are completely constrained motion, successfully constrained motion and incompletely constrained motion. In completely constrained motion, when motion between two elements of a pair is in a definite or a single direction irrespective of the direction of force applied, it is known as completely constrained motion. For example, the piston and cylinder in a steam engine form a pair and the motion of the piston is limited to definite direction relative to the cylinder irrespective of the direction of motion of the crank. Other examples are square bar in a square hole, shaft with collars in a circular hole, etc. In successfully constrained motion, when motion between two elements of a pair is possible in more than one direction, but made is to have motion only in one direction by using some external means, it is called successfully constrained motion. Consider a shaft in a footstep bearing as shown in the figure. The shaft may rotate in a bearing or it may move upward. This is a case of incompletely constrained motion. But if the load is placed on the shaft to prevent axial upward movement of the shaft, then the motion of the pair is said to be successfully constrained motion. The motion of an IC engine valve and the piston reciprocating inside an engine cylinder are also the examples of successfully constrained motion. Now, incompletely constrained motion. When the motion between the elements of a pair is possible in more than one direction and depends upon the direction of force applied, it is known as incompletely constrained motion. Here the change in the direction of the impressed force may alter the direction of relative motion between the pair. A circular bar or shaft in a circular hole as shown in the figure is an example of an incompletely constrained motion, as it may either rotate or slide in a hole. These both motions have no relationship with the other. The completely constrained and successfully constrained motions are generally known as constrained motion, and the incompletely constrained motion is known as the unconstrained motion. Now we are going to discuss about kinematic pair. A kinematic pair is a connection between two links form a pair, but this pair will be only a kinematic pair when the relative motion between the link is a constrained motion. And a kinematic pair are classified based on the type of relative motion, type of contact, and type of closure. Based on the type of relative motion, kinematic pairs are classified as turning pair, sliding pair, rolling pair, screw pair, and spherical pair. Turning pair. When one link has turning or revolving motion relative to the other, they constitute a turning or revolving pair. For example, circular shaft revolving in a bearing. Next one is sliding pair. If two links are having sliding motion relative to each other, they form a sliding pair. Example, a rectangular rod in a rectangular prism, piston cylinder arrangement, etc. When the link of a pair having a rolling motion relative to each other, they form a rolling pair. Example, a rolling wheel on flat surface, ball and roller bearing. Screw pair or a helical pair. If two mating links having turning as well as sliding motion between them, it form a screw pair. Example, lead screw, nut of the lathe, etc. When one link in the form of a sphere turns inside a fixed link, it is a spherical pair. Example, ball in socket. Now, based on the type of contact, kinematic pairs are classified as lower pair, higher pair, and wrapping pair. Lower pair is a pair of links having surface or area contact between the member. Example, nut turning on a screw, shaft rotating in a bearing, or pair of slider crank mechanism. When a pair has point or line contact between the links, it is known as higher pair. Example, wheel rolling on a surface, cam and follower contact, etc. A higher pair involves two dissimilar surface contacts. All lower pairs are closed pairs. And the next one is wrapping pair. When one link is wrapped over the other link, it is called wrapping pair. For example, belt pulley system. Wrapping pair is more close to higher pair. Now, based on the type of closure, it is classified as self-closed pair and forced closed pair. When the element of a pair held mechanically, it is known as closed pair. The contact between the two can be broken by only destruction of at least one of the members. All lower pairs are closed pair. Okay, next one is forced closed pair or unclosed pair. When two links of a pair are in contact either due to force of gravity or some spring action, it is called a forced closed pair or unclosed pair. Example, cam and spring loaded follower. Now, type of joints in a mechanism. There are mainly three types of joints in a mechanism. They are binary joints, ternary joints, and quaternary joints. If two links are joined at the same connection, it is called binary joints. If three links are joined at a connection, it is called ternary joint. It is considered equivalent to two binary joints, since fixing of any one link constitutes two binary joints. Next one is quaternary joint. If four links are joined at a connection, it is a quaternary joint. It is equivalent to three binary joint. And always remember, if n number of links are connected at a joint, it is equivalent to n minus 1 binary joints. Now let us discuss about kinematic chain. So what is a kinematic chain? When all the links are connected in such a way that first link is joined with the last link, then the structure formed is known as closed chain. The closed chain will be a kinematic chain when the relative motion between the links is either completely constrained or successfully constrained. A kinematic chain forms a mechanism and a mechanism forms a machine. Now talking about degrees of freedom or mobility, it is defined as the minimum number of independent variables required to define the position or motion of the system. The degree of freedom of a closed chain can be determined by Kutzback's equation and is given by F is equal to 3 into L minus 1 minus 2J minus H, where L is the number of links, J is the number of binary joints, and H is the number of higher pairs. Now, look into the figure given. Here, the number of links L is equal to 3 and number of binary joints J is equal to 3 and number of higher pairs H is equal to 0. Now, substituting these values in the Kutzback's equation, we will get F as 0 and such a system is known as structure. Now, moving to the next figure, here the number of links L is equal to 4, number of binary joints J is equal to 5 and there are no higher pairs in this given figure, and so that H is equal to 0. Now substituting these values in the Kutzback's equation, we will get F is equal to minus 1 and such a system is known as superstructure. And moving to the next figure, here L is equal to 4, J is equal to 4 and there are no higher pairs in this figure 2 and we will get F as 1 and such a system is known as kinematic chain. Now let us talk about Grubler's equation. Grubler's explained that to convert any linkage combination in a kinematic chain, the following equation must satisfy. That is 3L minus 2J minus 4 is equal to 0, where L is the number of links and J is the number of binary joints. This explanation is given for those mechanisms whose F is equal to 1 and H is equal to 0. That is, degrees of freedom is equal to 1 and number of higher pairs are 0. The minimum number of links required to form a mechanism is 4. Next, we can discuss about 4-bar mechanism and its inversions. A 4-bar mechanism consists of 4 links and 4 turning pairs. And an inversion is a mechanism which are obtained by fixing different links one by one. The main inversions that are obtained from a 4-bar mechanisms are double crank mechanism, crank rocker mechanism, and double rocker mechanism. Greshoff's law helps us to predict whether one part can rotate continuously or not. We apply the criterion to 4-bar kinematic chains that are joined with pin joints. A Greshoff mechanism has at least one part that rotates continuously. And Greshoff's law states that for the continuous relative motion between the links in a 4-bar mechanism, the summation of the lengths of the shortest and longest length should not be greater than the summation of the lengths of other two links. That is, S plus L less than or equal to P plus Q. Talking about Greshoff's law, there are mainly 3 different cases. First one is S plus L less than P plus Q. And if the shortest link is fixed, we can obtain a double crank mechanism, and if the link adjacent to the shortest link is fixed, we can obtain a crank rocker mechanism, and if the coupler link is fixed, we can obtain a double rocker mechanism. The second case is if S plus L equal to P plus Q. In such cases, 2 types of linkages are formed. First one is deltoid linkage and the next one is parallelogram linkage, and the final case of Grashof law is S plus L greater than P plus Q. Here Grashof law is not satisfied, and if any link is fixed, it forms a triple rocker mechanism. Here none of the links make a complete revolution, and that's the conclusion